Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, welcome to Technical Session 14D. I'm Pranjal Banage, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, ICICT 2026 in London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held on 24th Feb in London, UK, and the virtual event is being held through Zoom from 25th to 27th February 2026. I hope you'll enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for their presentation and 3 minutes for question and answers. In 10 minutes, I'll raise a gentle reminder. There's another request to all the participants that you all stay connected with us till the closing remarks. If you have any queries or updates, then you can write it to me or to my co-host in the chat box. Now, before we start the session, I would like to introduce you all to the session chairs of this session. I would also like to apologize in advance if I mispronounce your names. Starting with Norsahira Khairul Anor. She is a research officer at National Energy University located in Malaysia. Her key areas of expertise include data analytics and privacy preserving mechanisms, contributing to research and innovation in data driven and secure computing solutions. Ma'am, would you like to give a few opening remarks?
Hello everyone. Welcome to this ICICT 2026. I'm Shahira Karanwa from University Tenaga Nasional Malaysia, and it is my pleasure to serve as the session chair together with Dr. Sonali Timali. So in this session, we will have several interesting presentations that covering different topics in information and communication technology, including artificial intelligence, healthcare application, IoT system, and energy system. So I hope that all the presenter can present their contribution. Thank you.
Thank you so much, ma'am. Moving forward to our next session chair, Dr. Sonali Mai. She is an associate professor in the Department of Information Technology at Bharati Vidyapeeth College of Engineering in Pune, India. She specializes in object-oriented modeling and design with academic and research interests spanning various areas of information technology. She is actively involved in teaching and research, contributing to the advancement of IT education and practice. Ma'am, would you like to share a few words?
Yeah, Pranjal, thank you very much for introducing me. I am very glad to have in the capacity of session chair and for attending this session. I wish all the best for all the presenters and researchers for their upcoming presentation. Thank you all of you. I am presenting here on behalf of Bharati Vidyapeeth Dimdu University College of Engineering. Thank you for calling me here for this conference. Thank you.
Thank you so much, ma'am, for those words. Next up, we'll start with our presentations. First, I would like to call upon Muhammad Azab to present his paper on adaptive R-way detection in scalable ECG databases towards biometric identification. You may share your paper by presenting your screen.
Okay. Good evening, estimated members. I am Muhammad Azab, PhD researcher at ITMO University. Today, I will present my work on R-wave detection for scalable ECG-based biometric identification. Biometrics are moving beyond traditional methods with physiological signals gaining attention due to their inherent security. Rapid market growth reflects the increasing demand for secure and continuous authentication driven by advances in artificial intelligence. Among different biometric modalities, we focus on ECG because it provides some intrinsic liveness detection and strong resistance. The unique structure of heartbeat provides stable and distinctive features, making it highly suitable for secure authentication. However, ECG authentication strongly depends on accurate R-wave detection, a real-world large-scale databases, noise, device variability, and different sampling rates makes this task highly challenging. Therefore, a unified, robust pipeline for R-peak detection is essential for scalable and reliable biometric authentication. Our main goal is to achieve accurate and efficient R-wave detection across heterogeneous ECG recordings. And to accomplish this, we design a scalable database-oriented architecture and develop a low-complexity detection algorithm validated on benchmark datasets. To address heterogeneity, we propose a four-layer architecture. Our system integrates multiple ECG sources, standardizes them into a unified representation, and stores them in a centralized database. This ensures scalable processing and consistent R-wave detection for identification. In this stage, heterogeneous ECG datasets are parsed, resampled, and enriched with metadata to ensure structural consistency. All signals are then converted into a unified internal representation and stored in a centralized database. This ensures consistent storage and enables scalable downstream processing. Second, after standardization, we apply adaptive thresholding mechanisms that detects candidate R peaks and validates them using physiological refractory constraints. The threshold continuously updates it to maintain stable detection performance under varying signal conditions. To validate generalization, we use two benchmark ECG datasets, which provide different recording setups and a structural format. This allows us to assess detection stability across diverse ECG environments. We evaluate performance using detection accuracy, precision, recall, to measure current detection, false positives, and missed beats. In addition, we assess computational efficiency through average execution time to ensure practical scalability. The proposed detector was evaluated on both ECG ID and MIT BIH datasets, and we could achieve higher accuracy for our peak detection using these datasets. Performance improved, and we could achieve balanced precision and recall. In addition to high accuracy of detection, our approach achieves nearly 3 times faster processing than Tompkins, making it more suitable for scalable and real-time biometric systems. In conclusion, we developed a scalable ECG database architecture combined with adaptive R-wave detection algorithm, achieving high accuracy under varying ECG conditions. The lightweight and the self-adjusting design makes it suitable for real-time biometric deployment. But beyond ECG, the proposed architecture provides a generalizable framework and for scalable physiological biometric systems, supporting future integration with multi-lead processing, machine learning models, and large-scale population validation. Thank you very much for your attention, and I will be happy to answer any question.
Yeah, Mohammed, I have one question. It is regarding the your adaptive threshold mechanism you mentioned there, right? And as per its your discussion, it ensures the robustness and stability of the R wave detection, right? But however, these R waves are very sensitive to some of the variables related with the physiological changes like stress, exercises, and all those. How does your this adaptive mechanism is going to ensure the stability of this RWF detection in such kind of scenarios?
Yes, we could test our proposed solution on different data sets, MIT, which includes healthy and non-healthy ECG recordings, and the ECG ID, which includes totally healthy recorders. So we actually have different sampling rates, we have different setups, we have different leads for recording these signals. So even after that, when we could design our database, design our schema, we could sampling and we could standardize that using MFPR representation, and then we could implement four data tables in our database, which after that, when we need to re-authenticate, it will be more faster. So yes, maybe I need later to increase the testing to the other datasets to ensure more stability and robustness. But from these results, we could achieve something like different unified database and adaptive R-wave detection based on data sets we used.
Yes, right. So it's a good start for the this, but this real time adaptation for adaptivity, we should try it on the real world in real time scenarios. Yes.
Yes, that's why we could have performance less than 2 seconds
Mm.
comparing to Pumpkin, which gives us a chance and opportunity to apply these methods in practical world.
Yeah, right. Thank you.
Thank, thank you.
Okay, hi. I have one question for you. What are the main challenges when using ECG signal for biometric identification in real-world scenario?
I have proposed in telehealth, like remote patient monitoring and accessing every patient can access his own data, or during monitoring a session, so we could have some kind of continuous authentication using ECG. And I could propose a practical solution for that, but generally in the area of telehealth.
Okay, thank you.
Thank you.
Thank you so much, sir, for that insightful and interesting presentation.
Thank you very much.
Next, I would like to call upon our next presenter, Karishni Kuber, to present her paper on advanced IoT-driven real-time train tracking through LoRa telemetry and cloud stream analytics. You may present your paper by sharing your screen.
Hi, just give me 1 minute. Good morning, good afternoon, everyone. So, we are going to present a paper on advanced IoT-driven real-time train tracking through LoRa telemetry as well and cloud stream analytics. I'm Karishni, and our presentation would be presented by Himanshu Tenagi, Karappa Baba Suraj, Kamya Mudalyar, Karishni Kuber, and under the guidance of our professor Animesh Giri. So our problem statement is that traditional train tracking systems rely on GSM networks or manual updates. These lead to delays, coverage gaps, and high operational costs, especially in remote areas. So this project aims to develop a cost-effective real-time train tracking and collision detection system using LoRaWAN. The trains will be equipped with a bolt-on solution with GPS modules and LoRaWAN transceivers to continuously broadcast location data, enabling real-time train tracking with high accuracy. Our trackside gateways will receive this data and forward it to a cloud-based Kafka infrastructure where Apache Flink will process it to detect potential collisions. The system will provide continuous visibility to train movement, thereby reducing dependency on cellular networks and enhancing railway safety by enabling timely alerts and efficient management. So, moving on to our abstract, the challenges in the traditional train tracking system, as discussed before, is that traditional train tracking systems rely on GSM networks and manual updates. These lead to very high operational costs, especially in remote areas. So, our proposed solution is that this project introduces a cost effective real time train tracking solution leveraging LoRaWAN, which is a long range, low power, and low bandwidth communication protocol. Our key features is that our trains would be equipped with GPS and LoRaWAN transceivers, thereby receiving real-time encrypted location data to our trackside gateway, which forwarded to our Kafka-based cloud infrastructure. The impacts and benefits of this project is that the system ensures continuous train visibility, minimum GSM dependence, and reduces operational costs, thereby enhancing railway safety through real-time alerts.
This is the architecture for our project. Our project contains four modules: the train side module, the track side module, the core backend, and the client handler. The train side collects the GPS coordinates and then sends it to the track side, which is picked up by the LoRaWAN module, which is then further sent it to the Kafka broker, then on to the core backend, which is then sent to the front end via WebSockets. This is the train side module. The train side module comprises of the u-blox GPS module and the LoRaWAN module. Both of them are connected to the Raspberry Pi via FTDI chips. The u-blox GPS module gets the latitude and the longitude, the coordinates, and then sends it to the Raspberry Pi. After some pre-processing, the Raspberry Pi then sends it to the LoRaWAN. The LoRaWAN will then broadcast this data, which will then be picked up by the trackside LoRaWAN module. After being picked up, it will then send it to the Raspberry Pi, which will further send it to the Kafka broker via a public IP address.
Okay, so this slide presents the cryptographic handshake mechanism that we have used. We are implementing an X25519 encryption. So it's a elliptical curve Diffie-Hellman key exchange. And due to the properties, both yield the same shared values without transmitting their private keys. So the terminal output shows like successful handshake and shared key derivation on both ends. Yeah, in the coming slide, we'll see live GPS telemetry is published on the Kafka topic, and we're using Apache Flink to continuously consume the stream using a defined consumer group and an offset strategy. So what the processor is doing is it's persisting the data into a timescale DB for long-term analysis, and then it is updating Redis with the latest train state for real-time access. Uh, okay, so this slide is explaining the real-time client communication. We are using fast API based server that bridges Redis channels and WebSocket clients. So we have a global Redis pool that ensures concurrency and efficient resource management. So the system is distributed across three DigitalOcean droplets. That is broker node, backend node, and front-end node. So we are hosting Kafka for ingestion separately, and we are running Flink, Redis, Timescale DB, and Fast API on the backend node. And for the front-end node, it serves the client application with Node.js and Nginx. So the separation it isolates ingestion, and computation and presentation layers. So this is like a modular deployment. So it ensures workload isolation and support for sustained real-time streaming.
All right. So now coming to the testing and the benchmarking process, and we'll just walk through how we have benchmarked our system. If we have to measure the one-way latency. So let's say we only care about the latency going from the train side till the client. We don't care about the round trip latency. When we started measuring this, what we understood is even though two clocks on two different systems, they might show the same time. What happens is there is a slight microsecond to a nanosecond difference, which is known as clock drift. And when since we are measuring one way, that millisecond difference will throw off our calculations by a lot, So next slide. So now what the architecture which we've gone through is known as the single source of truth, where for testing the latency between the train side and the track side modules, what we did is the train side module initially queries another system on the network to get the current timestamp, and it sends the timestamp to the track side, and the track side queries the clock system again and subtracts it to get the latency. In this way, there is one single source of truth, and we don't have to jump, and we don't have to say that either a train side or track side has the right time. What this and When we checked out the latencies between the train side and the track side modules, we see that latencies, previous slide, we see that the latencies are between 30 milliseconds, and they jump only up to 62 milliseconds. And this is consistent with how LoRaWAN behaves, since it's a low latency, low bandwidth network protocol. Now, when we come to and we measure the entire system, we see we adopt a similar architecture, but in this case, we also need to factor in the network latency, because the clock system is no longer on a local network, it's on the global network. The core backend and the train side query the same clock system, but we do need to factor in the network latency, which we estimate to be approximately from 100 to 200 milliseconds. And when we measure the latency from train side to core backend, in our results, we have found that uh, next slide. In our results, we have found that the latency was between 600 to 800 milliseconds, and this is without factoring for the network latency, which we believe does play a huge role. We did notice a few minor fluctuations where, on deeper investigations, we found that the Redis cache limit we had set, it had blown through it. So Redis was busy trying to clear its cache, and then we noticed that the latency was coming back up again. And our architecture is a very decoupled type of architecture, right? So because of that, we have seen that even if there are multiple concurrent data streams happening, if we have multiple brokers and they're set up across different regions, we see that and they're set up across different region, then in that case we can do that. Next one. Okay, so now this is a short demo where we can see that the train side is sending data to the track side, and the track side is sending data to the Kafka broker, and the Kafka broker sends it to the core backend, and this is all happening in real time. And now when we go to the next slide, we can see that as soon as we start the tracking, we want to get the most accurate GPS coordinates possible. And we can see that the place where the testing was going on, which is near a college, we see that they both happen at a similar, like the Google Maps coordinates and us. This is the testing module which we had built. And next. So this is our front end which we have built. It is using Leaflet.js, and it is rendering the map in real time. So it's updating the map in real time. As you can see, the coordinates are being updated in real time, and they're being received by through WebSockets from the core backend. So coming to the conclusion, we can see that the modern world is being the digital transformation is happening in real time, and it's happening very quickly. And we need for a lot of people, tracking trains accurately and with the most minimal latency possible, and in a cost sensitive market like India, we do believe that going with a low cost but an effective solution that gives us the results that we want. And our proposed architecture gives us a cohesive real time monitoring product. And we also, through our architecture, we have demonstrated that we have integrated multiple technologies like IoT, where we have used Raspberry Pis, and LoRaWAN technology, and also stream analytics such as Apache Flink, and we have also used Redis. So all of these combined into one unified framework, we have shown that this works, and we have built it in such a way that any technology can be swapped out. Like, let's say tomorrow we want to switch to some other type of technology, like other than LoRaWAN, some other new type of technology comes, we can switch it over. So this is our project, and we'll be happy to take up any more questions.
Yes, may I?
Yeah, sure.
Suraj,
Yes.
you have nicely presented the work. It's a good work. I could see that you have very well handled the LoRaWAN, uh, what you can say, the limitations of the LoRaWAN. The latency issue is very well handled by your work. However, this GPS
Right.
is signal may get suffered from some of the inaccuracies in some at some places like tunnels or some dense areas, or maybe some adverse weather conditions may affect the GPS signals. So how are you going to take care of this missing the signal?
Okay, so coming to that question, we have actually considered it. So right now, the modules that we have access to, we have those modules only have access to one network of satellites, which is the GPS network, the original network created by the US. But now we have many more networks, such as the GLONASS, and one Europe has created, one India has created. So I believe that once the tunnel problem is essentially something that we cannot solve, because inside a tunnel, the signals cannot go outside. But if we have if we have this one, if we have a strong satellite connection to multiple satellites, and we
Mhm.
have LoRaWAN trackside stations inside the tunnels too, then we can get the data, and there'll be a small blackout period, but as soon as it comes out again, we'll start streaming. So yeah, with multiple GPS networks, I think we can handle this issue to an extent, but this cannot be solved completely because we there's no way to get the
Mhm.
data.
Thank you.
Thank you.
Ms. Amar, do you have any questions for them?
I have one question. Um, Thank you for your interesting presentation. So, how do you think this system can benefit the target user or the community?
I'm so sorry. Could you please repeat the question?
How do you think this research can benefit the target user?
Benefit
The target user.
the population?
Yeah.
Right now, we a lot of train systems around the world, they are plagued by delays, and we don't know when to reach the station, or sometimes we just want to track where the train is so that we can plan our day better. The original inspiration for this was Flight Radar 24, which can track flights in real time using ADS-B data, and we wanted to have something for the Indian market where we could. Where in India we do face sometimes there are train delays, and we want to track those trains so we can plan our day better, we can save our time, and this is just to show that in a low cost we will be able to deploy this.
Yeah. All right. Thank you.
Thank you so much for your time.
Thank you so much, guys, for this well-structured and enriching presentation.
Thank you.
Thank you.
Now, I would like to call upon our next presenter, Miss Lakshmi. Miss Lakshmi, are you there? Unfortunately, it seems that she's not with us, so we'll be moving forward with our next presenter, who's going to be Daniel Kwok.
Hello, I am available.
Yes, I would like to introduce him by saying that his paper that he'll be presenting on would be on evaluating artificial intelligence for chest X-ray analysis in a low prevalence outpatient setting, a multi-reader, multi-case study. You may share your paper by presenting your skill.
Perfect. Maybe just on the introduction, can you see my shared screen, please?
Yes, sir, we can see your screen.
Perfect. Thank you very much. Good afternoon, everyone. My name is Daniel Kvak, and together with the team of Dr. Klara Zezulova and Dr. Jakub Dandar, we'll be presenting the work titled Evaluating AI for Chest X-ray Analysis in a Low Prevalence Outpatient Settings. The key of our study is quite practical because outpatient chest X-rays are being very common, but clinically significant findings are relatively rare in the clinical practice. And they create a specific challenge for both radiologists and, of course, artificial intelligence assessment teams as well. As a bit of an introduction, chest X-ray imaging is used routinely in outpatient clinics, so not only large university or regional hospitals, but also smaller clinics as well, often as a first line of examinations. But in these settings, typically the prevalence of any meaningful abnormalities is quite low. So the question is quite simple. Most of the artificial intelligence solutions in the current clinical practice are being tested in the hospital setting, in the hospital environment. But we want to ask if the AI system can be still useful where the base rate of the abnormalities and the prevalence is small and is low. In our study, we evaluated the commercially available artificial intelligence software for automated chest X-ray analysis, CareBot AI Chest X-ray, developed by CareBot company from Czech Republic. Our primary objective was quite straightforward. It was to assess the diagnostic accuracy of AI in a routine outpatient population to determine whether it performs comparable to radiologists and with the longer-term goal of reliable decision support and improved workflow efficiency without compromising the safety of the patient. In a low prevalence setting, even the high performing tool can look a bit different depending on the metrics that we will be using. And that comes into the methodology slide. So we were doing a single center retrospective multi-reader multi-case study, so MRMC study of the 215 consecutive outpatient posterior anterior chest X-ray images that were acquired over a week time, and 6 board certified radiologists with 1 to 9 years experience, and the AI system commercially available, independently and blinded, assessed 4 different pathological findings: atelectasis, consolidation, pleural effusion, and pulmonary lesions. In the readers, we were using a reference standard. We used a consensus of the 2 RATIC radiologists, and any disagreement findings were afterwards sorted and fared by third adjudicated thoracic radiologist. For the analysis, the outputs we are using were binary findings, so present or absent, so the performance could be compared between AI and radiologists, and we computed the typical diagnostic method. So sensitivity, specificity, positive and negative predictive value, all together with 95% confidence interval. And importantly, we compared AI versus each radiologist using paired Magna-Mark test, looking at the per K differences. Regarding the demography, we can see that the prevalence of the individual pathological changes was quite low, exactly as we would expect in the ambulatory outpatient clinical cohort. So out of the 213 chest X-ray, we found atelectasis in 15 cases, consolidation in 13, pleural effusion in 16, pulmonary lesions in 7. And this matters because with such low prevalence, the positive predictive value will be almost inevitably lower, even when the sensitivity and specificity are strong, simply because false positive will outnumber the true positive when the positive are rare. On the other hand, the low prevalence tends to make NPV, negative predictive value, high, and that is the key reason why outpatient settings are especially interesting for AI as a rule-out procedure. So a second reader system that is able to sufficiently disregard the negative findings. If we start into the results, we can start with the artificial intelligence performance. So across the 4 findings that were discovered in this study, the sensitivity of the artificial intelligence was ranging between 80 to 100%, with the specificity ranging from 92 to 98%. What's very important is that the negative predictive value was nearly perfect for the individual findings. So it was 99 to 100%, and that means that we can use the solution for a strong rule-out capability. As expected, the positive predictive value was lower, which is very typical in the low prevalence settings. So typically, for the typical pathological finding, such as pulmonary lesions, the positive predictive value was around 26.1%. That doesn't mean that the artificial intelligence is not strong in that. It means that in a settings when the lesion findings are rare, a positive AI flag should be always interpreted as please look carefully at the finding. The table also summarizes the 2 robust metrics that we chose for imbalance data, and that is the balance accuracy. And we also did a Matthews correlation coefficient. For balance accuracy, AI was higher than the mean of radiologist performance in all findings, and it was also statistically significant higher for atelectasis and for pleural effusion. For pulmonary lesion, the difference was not statistically significant because probably it was the limiting number of positive pathological findings. Regarding radiologists, we can now take a look at the outcomes. Typically, radiologists showed very high specificity, ranging from 90 to 100%, and a very high negative predictive value, ranging from 94 to 99%, which is quite reassuring. But the biggest variability we saw not on the side of the negative predictive value or specificity, but on the side of the sensitivity, which varied widely from around 20% to 87.5%, depending on the finding and the reader. In other words, subtle findings such as small lesions or mild linear atelectasis were missed by some readers, while others were able to spot these findings. The variability also strongly suggests an effect of a reader experience and interpretative threshold, especially for the subtle findings. And this is, of course, where the artificial intelligence strong part is actually coming through. On the slide, you can see forest plot summarizing sensitivity on the left and specificity on the right. But you can see that AI is showing constantly high sensitivity and high specificity. And of course, you can also see that the 95% confidence interval were very strong for the specificity part, and of course, then for the negative predictive value, but not very representative for the sensitive part instead. If we take a look on the detailed tables, we can see that the main takeaway, which is AI is within the range of the radiology performance, typically on the higher edge, often comparable and in some settings showing very strong rule-out behavior through very high negative predictive value. And of course, the PPV still remains limited by the individual pathological prevalence on the individual findings. If we take a look on few of the AI outcomes, we can see multiple different pathological changes in such as in this report, we can see in the apical region the presence of a small pulmonary lesion, which the artificial intelligence is able to spot, which is quite a tougher pathological finding for individual radiologists. On the second image, you can see a small linear atelectasis in the pleural effusion part where the pathological findings are often being missed or discharged by individual radiologists. On such image, you can see, for example, in the younger patient, just seeing from the individual structure of the patient's body, you can see a very typical pneumonia pathological change, which was labeled as a consolidation by all the radiologists and also the artificial intelligence solution. While here on the right part of the lung parenchyma, you can spot again a small pulmonary lesion, which is probably benign, but the artificial intelligence is able to spot even such small pathological changes. Or in this case, where we can see blunted costophrenic angle on the left side of the patient, which can be indicative of the newly appearing pleural effusion, as well as small linear atelectasis change, which the artificial intelligence solution is able to spot. And on the other image, you can see bilaterally pleural effusion present with the blunted costophrenic angles. Whether it's being from decimation or pleural effusion, it's hard to detect, but also some small linear atelectasis, which the AI is able to spot on that side. As the conclusion, the most important result for us was the near perfect negative predictive value from 99 to 100%, which means that the AI can very reliably identify normal, negative, or we can call it low risk outpatient chest X-rays for the findings that we are able to evaluate. And this supports the use as the effective second reading decision support tool, for example, for triaging of the individual patient or so on in the routine outpatient practice. In the terms of the workflow impact, normal AI reads can increase confidence in individual pathological changes and reduce unnecessary escalation of the individual pathological changes for this patient. And of course, AI flagged cases might prompt more focused review on the pathological changes. So overall, in this MRMC study, the AI performed on par with individual radiologists and might be able to improve efficiency without compromising the safety of individual patient, particularly as a rule-out second reader in the outpatient clinical settings. And this is just the bibliography from my side, and that would be all. Thank you very much.
The session chair, do you have any questions for him?
Yeah, one question. Thank you for your presentation. How do you see AI supporting doctors in medical image analysis in the future?
Absolutely. So I think that's a good question and very, very responsible question. Unfortunately, we only have 3 minutes because this is definitely a good topic for a couple of hours. But to be honest, from what we see in the clinical practice, artificial intelligence solution and medical imaging are being spread quite widely, but we're still more or less looking at the more targeted solution, like typical specific findings, typical pathological changes. And I think we're still in the same narrow procedure that we were able to have from around 15, 20 years before. So I think that in the near future, we can start seeing any multimodal approaches, including generating the clinical text, but also correlating it with the clinical practice. Meaning, for example, right now the artificial intelligence will spot a consolidation, but the radiologist or the pulmonologist will have to define what kind of pathological outcome it actually is based on the clinical correlation. Like, is it a pneumonia? We can only determine based on CRP or clinical history of the patient or follow-up imaging or so on. And this is where I think that artificial intelligence is still just at the start and will need a more space and more focus in the near future.
Okay.
Yeah, Daniel, thank you for your presentation. I have one question. Since it is your AI has demonstrated a very high in NPV, right? Can you just go to back to the results you have received from the AI
Of
NPV?
course, of course. So the typical outcome of the artificial intelligence from last couple of years was basically the doctors don't care about false positivity. They don't care about specificity. But we found out that's actually not true. From my clinical practice, any false positive alarm, especially on multiple different pathological changes such as infiltration or suspicious lesion or even say pneumothorax, will actually
Mm-hmm.
start preparing me for multiple different diagnostical procedures. And the differential diagnosis, of course, remains very complex on the side of the patients. So the
Mm-hmm.
typical outcome that we were able to spot is very often we can see that the patients or the artificial intelligence solutions are being tested on standard local population in the hospital settings. And in the hospital settings, I would say it's around 50-50. 50% imaging will be negative, pre-operation ones or so on, or just control images and so on, while the half of it, at least half of it, will be positive with multiple pathological changes, such as from internal medicine, pulmonology medicine, emergency department, and so on. And the difference between the outpatient settings is very nicely visible. So in outpatient settings, usually if you cough for just few days longer than you would imagine, your GP will automatically send you for the X-ray examination. And in this case, you're entering outpatient clinic. So the outpatient clinic is usually, I would say, 90% or even more, 95% the negative imaging. And this is basically one of the spaces where artificial intelligence is not being tested so widely because it can still do a lot of false positivity. Typically, stronger pulmonary markings, stronger vascular markings, stronger hilar prominence, different kind of mimics, such as mamilla being reported as pulmonary lesion or so on. And this is basically why we structured the cooperation with the outpatient clinics as well, because we were kind of focusing that at least 90% or something like 85-90% of the pathological changes will remain negative. So this was our intention with the individual study, and the outcomes that we were able to achieve were basically on par with individual
Yeah.
radiologists, which is quite surprising because typically artificial intelligence tended to overpromise, overdiagnose individual pathological changes.
Mm-hmm. Yeah, right. Okay, so this aspect has been considered from your side, right? Okay, thank you.
Thank you very much.
Thank you so much, Daniel, for that impactful presentation.
Thank you very much.
Uh, we'd like to move forward. I'll be calling upon our next presenter, Ali Tahir Hamid, to present his paper on optimized droop mechanism technique for islanded microgrid system. Sir, you may start your presentation by sharing your screen.
Firstly, good evening to everybody.
Good evening, sir.
Did you see my screen, please?
Sir, I don't think you can see your screen.
So now, is it working now?
Can you please try again?
I'm presented now. I make it. I presented now. It is working. Please.
I don't think so, sir.
I think it is only share. Is it working now, please?
Yes, sir. We can see your screen now.
Yes, it's okay. First of all, I want to thank ICICT 2026. My name is Dr. Prof. Ali Tahir Hamid. I am one of staff of University of Diyala College of Engineering and Dean of University of Rafidain University College in Iraq. This working has been generated from five authors from Iraq and Bahrain. This is from me and Dr. Inas and Dr. Noor and Dr. Shahid Al-Yusuf from Bahrain. Firstly, we want to explain this project. It has been one of a huge project, has been make it one of these topics. It's optimized drop mechanism technique isolated. This is abstracted due to the difference feeder impedance. On the other characteristics that isolated microgrids, conventional SAG regulator algorithm were unable to providing sufficient reactive energy distributed to define SAG constant and improved SAG regarded mechanism presented to this publication based on the total load and eventual capacities for each inverter. So the central control collected as a percentage to the power, reactive power value that transmit to each inverter units. So here, this has been made a simulation by using a platform from MATLAB. So the goals of this research is to improve the useful guide to real-world use to microgrid control systems. So introduction, one, wait, just I want to, that's okay now. So one, excuse me, is the sharing is working now? Is working properly? Is that right? Please. Hello? It is working now properly, right?
Yeah, the slide is in introduction.
Yes, it's great. One of the effective solutions is to develop the energy solution that distributed generated DG, it means distributed system microgrid when the emphasis DG electrical sage and control technology can operate both in grid connected and isolated state. In grid connected configuration, voltage and the frequency are regulated by the main network, while the isolated set up load distributions among these generators or dispersed generators can lead to change or challenge such as reactive power among imbalance due to the different line impedance. This is a very important topic to the line impedance. This can affect grid reliability and power quality. Various strategy for active power allocation has been suggested, including harmonic injection into DG output and control mechanisms. However, this method may encounter stability issue under the certain condition. So to enhance this distribution for reactive power without need a price line impedance measurement, this research proposed an improved drop control framework that adapt to change in load condition, aiming for fair allocation across inverter while maintaining system stabilities. So methodology, you can see figure number one, arranging the simplified isolated microgrid. So for conventional mechanism, you have to know what is the SAG regulator analysis. So figure one, number one, explain the configuration, systematically describe the isolated design that examined in this research inverter and use strategy for distributed generated without, as shown in reference number 13. Since the chief emphasis and mentioned study for superior distributed electrical energy, also the power distributed for line load. The microgrid is mentioned by the central control, so also distributed. You can see in the figure number one, you can see the impedance and resistance. And both of them that be connected in the, you can see here, and PCC that will be connected to go to the line. So you have to use two module or two equations for omega I and U for I. So traditional drop mechanism employ the microgrid module, produce the voltage, and each inverter connected up on this and to protect to all of them. So the SAG mechanism can be calculated by these two equations. You can see also for every topic or every point in this module, as shown in figure number 2, structure and conventional drop control. You can see the power collections and as shown here, and this summations for all of them to make voltage and current to drop voltage. So this will be shown the stabilities. You can see the reactive power and improve stabilities also. So in next one or next step, you have to know what is the reactive power distribution analysis. Without the microgrid, the power properly sometimes will be insufficient. So in constant voltage and local variables into the line impedance between distributed generating that DG, especially as unequal line length to the PCC, cause unequal reactive power sharing. So even if 2 DG has been identical capacity and the reactive power drop coefficient usual line lead to different voltage slopes. So the DG and higher impedance stepper voltage power curve and higher output voltage, so resulting in reducing reactive power contribution and unfair reactive power distributions. You can see in this figure number 4 equivalent the circuits model for 2 shunt DG. You can see here, and for this PCC and the load, you can connect DG1 and DG2. And you can see the process for DG1. This is impedance and resistance. So isolated. So isolated corrections circuit, the isolated microgrid is 2 distributed generation configuration for DG and are interfaced without the point sharing connection to the PCC via distinct line impedance. Though this figure you have to see in on it DG1 and DG2 and delta X1, delta X2, and you have to see AU1 and AU2 for everyone has been, this is as a coefficient for PCC. For figure number 5 shows the mechanism design that implement enhanced virtual impedance using integrated control and the DG regulated to the simulation resistive based on the variance aimed to the settled electrical energy production and the effective power circuit. Oriented value simulated reactive is overload up on the voltage references due to the delivered from drop mechanism when the virtual impedance is to extend the actual sensitive electrical energy. And next, for this figure, protect the DG aligns without the sensitive electrical energy oriented value, simulated resistivity value, case or the variety. So variable impedance or virtual impedance value subjected is to alertion so slowly with the there is no shift for power factor. You can see it in the figure number 5. It is very obvious. Now you have to see some result for this output of this article. You can see the simulated across it, the price is load distribution emphasis define the control mechanism as the DG capacitive variables and the factor utilities and the simulation for table number 1. You can see DC slide voltage, rated frequency, line impedance 1, line impedance 2, and the load, and the filter capacity C upon micro F and microfarad, and reactive load, and the drop control coefficient. So you have to see now some results. This result you have to, this is figure number 6, output voltage of the distributed unit 2 upon a drop control method. For since DG1 and DG2 has the same capacity, and this essential that active power distributed among these distributants generated by equal throughout the system, say steady state operation in order to enable allocation of active power when distributed generated is of equal capacity is run simultaneously using traditional drop control techniques. Figure number 7, this is the output of the distributed units, and we have to make some comparison between our work and the previous work. Shows that the generated CAN module, these output power according to active power, drop coefficient, both after and before load variation. So you have to see the distribution, the distributed generated output power response through figure number 7. You can see here. So for figure number 8, this is the output reactive power distributed for the DG may modulate their output power and reactive power drop coefficient. This is before fluctuation. You can see here the fluctuation is very working and very clear, and you can use when dual DG and identical operation simultaneously via the operated method as exposed in the figure number 8. Finally, we have to see conclusion. The traditional drop control cannot ensure the fair reactive power sharing due to impedance different in DG lines. Number 2, variation in the line sensitivity caused voltage diversion, landing, and to unequal reactive power distribution. The proposed work, improved drop control, does not require line impedance measurement. It is adaptively regulated virtual sensitivity according to line power. This compensates for line sensitivity variation to ensure the actuated reactive power sharing. Simulation result demonstrated superior performance compared with the conventional drop control. Finally, thank you for listening, and any questions?
The session chair, do you have any questions for him?
No question from my side.
I have one question. How does your method perform when there are sudden changes in load demand?
Sorry, repeat my question, please. I don't hear it, obviously.
How does your method perform when there are sudden changes in load demand?
This is a very good question. So actually, for this result of this method, we proposed improved control framework to attack this issue related to reactive power distribution. So in each line impedance on conventional drop control scheme, this framework moved to need the direct impedance measurement and emit for unfair reactive power allocation to make this challenge.
Okay, thank you.
Thank you. Thank you so much.
Thank you so much, sir, for that engaging presentation.
Thank you so much.
Now, I'd like to call upon our next presenter, Rukmini Nazre, to present her paper on TerraCD multi-temporal framework for multi-class and semantic change detection. You may start your presentation by sharing your screen.
Is my screen visible?
Yes, your screen is visible.
Okay, thank you. Good morning, everyone. I'm Rukmini Nazre, and I'm a graduate student at UMass Amherst. And today I'll be presenting our work titled Terra CD, a multi-temporal framework for multi-class and semantic change detection. So I'll start with explaining why green space mapping is necessary. So urban green spaces provide many essential benefits. They help improve public health and mitigate the urban heat island effect and contribute to the United Nations Sustainable Development Goals. Another study conducted found that areas with higher urban vegetation are 3 to 5 degrees cooler than fully built environments. A study conducted in a variety of European nations which have strong environmental policies also found that they are struggling to maintain tree canopy. There's a rule called the 330-300 rule, which sets the standards for urban nature access. And the statistics tell us that the second metric, which is 30% neighborhood tree canopy cover, is the one that most cities fail to meet. So, what can be done to mitigate this problem? The first step is to monitor how much change is occurring and which regions are suffering the most. So, change detection is the way to do this. And our contribution is to create a benchmark data set for specifically for vegetation change detection. So, the current challenges which we faced are that there aren't many multi-class change detection data sets. Most of them only focus on detecting if something has changed. And even the existing multi-class datasets like HRSCD and SECOND actually do not focus on vegetation transitions. So this is an overview of the different methods which can be used for change detection. And we used all of these to benchmark our dataset. This is an overview of all the currently available change detection datasets. So I'll try to explain why TerraCD is novel. So as you can see, the first few datasets all just have one or two image pairs, which is not enough for large-scale change to occur. Then HRSCD, which is a prominent dataset, only focuses on France. And XBD and BDD are building damage datasets, so they do not focus on vegetation change. And second and high UCD, which are also large datasets, only focus on small regions like China and Estonia. Another thing is that high UCD, even though it's a large dataset, has a temporal span of just 1 year, which is not quite long enough for significant changes to occur. So with that in mind, we created TerraCD, and our focus was to have maximum geographical coverage. So our dataset actually covers 232 cities across USA and Europe. And we also decided to keep the temporal span as half a decade so that meaningful changes will be visible. So these are our objectives, and basically our problem statement was to create a bitemporal dataset of satellite imagery which supports multi-class as well as semantic change detection, and to benchmark it using the current change detection models. So this is how we came up with the acronym, Temporal Remote Sensing Repository for Analyzing Change Detection, TerraCD. And all of these images are one sample tile from TerraCD. So every tile contains an image from 2019, an image from 2024 of the same region, and land cover masks for both of these images. So in the land cover masks, dark green color represents dense vegetation, light green represents sparse vegetation, white color is built areas, and blue is water. And then these are two of our masks. So this one is for multi-class change detection, and it has three different classes. So no change, vegetation increase, and vegetation decrease. So the red color shows regions where vegetation has decreased, and green shows where it has increased. And the semantic change detection mask is actually more in depth. So it will classify every different type of transition, like dense vegetation to sparse vegetation, or dense vegetation to built area, as its own separate class. So there are 13 different classes in this semantic change detection mask. Now moving on to some statistics about our dataset. So we have 5221 image pairs, and we used Sentinel-2 imagery, and we picked an acquisition window of July to September for these images so that there won't be any snow. And we set the cloud cover threshold as 3%. So another thing is that since this image size is not large enough to cover entire cities, we chose to split the tiles into 9 different regions for every city as shown over here. Then this graph shows how many cities per country from Europe and cities per state from USA were included in our dataset. And the slide shows a few examples from different cities, and one row is one tile. Then this is an overview of our methodology. So first, we used the Sentinel-2 L2A product, and using Google Earth Engine's Python API, we obtained images from 2019 and 2024. Then these images were given to the SVM classifier to create land cover mapping masks. And then these masks were used to generate the change masks for both multi-class and semantic change detection. To ensure good quality of the dataset, we applied morphological noise filtering as well as statistical data cleaning. And then our dataset was ready. So this slide details how we actually got the land cover masks. So in order to classify in an image which pixel corresponds to, say, vegetation or water, we used these two prominent indices, NDVI and SWM, which are calculated as shown here. And then after calculating these indices, we used these rules to actually classify the points into these 4 classes: water, built area, sparse vegetation, and dense vegetation. And after annotating 50,000 training points per class, the SVM was able to classify all of these points in our images. And we manually validated them using the semi-automated classification plugin in QGIS. And this is what our land cover masks look like. So, and next, moving on to change mask generation. So these are just some examples of generated change masks and the different colors and classes for semantic and multi-class change masks. So we used these rules to classify whether there was a vegetation increase or decrease. So if anything moves from dense vegetation to sparse or dense itself, then there is no change. And if a pixel moves from built area to either sparse or dense, it is labeled as vegetation increase. And if it moves from sparse or dense to built area, we classify it as vegetation decrease, which is a bit not too specific. So instead of that, our semantic change detection masks actually classify every transition as its own different class, as you can see. So there are 12 different transitions plus the no change class. Now moving on to our data cleaning procedures. So first was morphological noise filtering. So the main goal of this was to remove salt and pepper noise. So by doing morphological erosion and dilation, we were able to get a filtered image which looks a bit like this instead of the noisy image which we started out with. Next, we also performed statistical data cleaning. So the goal of this was to have images which don't have a lot of no change pixels. So images with greater than 99.5% pixels of node change or with less than 80% pixels of node change were both removed from our dataset. And yeah, after the dataset was ready, we benchmarked it using current change detection models. So this slide details all of our training methodologies and our training setup. And our evaluation methodology was as follows. So we used a confusion matrix and a weighted metric as well, because SCD has a lot of class imbalance. And we also, so kappa was the main metric, and F1 score as well. And these were our results. So we used multiple methods like STANET, UNIT, LinkNet, DeepLab, as well as Siamese architectures. And our results are in line with those of other datasets such as HRSCD and SECOND. So this is how we benchmarked our dataset. And these are a few examples of the model's generated outputs on one slide from Cleveland. And yes, just to conclude, we created TerraCD, a benchmark dataset, which is the first large-scale vegetation-focused change detection dataset. And that's all. Thank you. I'll be happy to answer any questions.
Yes, Rukmini, can you name few more datasets which are vegetation focused?
Yes, so there isn't any specifically vegetation-focused dataset, but HRSCD and SECOND are the two closest datasets we could find. So HRSCD has a vegetation class and an agricultural land class, but it also has a lot of like built classes as well. High UCD is also another dataset. So yeah, high UCD.
Okay.
Yeah.
Apart from this vegetation, what are other use cases for which you can make use of this dataset?
It is mostly intended for urban planning and vegetation change detection. So that was our specific goal actually. So it can also be used to see where construction has increased for creating, say, a mapping of urban sprawl or for city census requirements, something like that.
Okay, that's it. Thank you, Rukmini.
Okay, thank you.
Do you have any more questions?
Another one question. How can this data set help future research in environmental monitoring or urban planning?
So this dataset can be used to train the models which can be used for change detection in urban monitoring. So models like Siamese networks and HRSCD strategies are the ones which are used to use deep learning for urban space monitoring. So this dataset will be a good training, will be good for training of these models so that they can be implemented for maybe real-time change detection or continuous monitoring.
Okay, thank you.
Thank you.
Thank you so much, Rukmini. We appreciate your time and efforts in putting up with such a presentation. Now, next, I would like to call upon Dr. Lakshmi to present her paper on effective heart disease prediction and classification using RNN with genetic approach. Ma'am, you may start with your presentation by sharing your screen.
Yes. Can you hear me, my voice, ma'am, now?
Yes, ma'am, we can hear you now.
Can you see my screen?
Yes, ma'am, we can see your screen too.
Yeah, yes. I'm Dr. Lakshmi. My topic is effective heart disease prediction and classification using RNN with genetic approach. Actually, heart disease is one of the major causes of death globally. Early prediction can help in timely treatment and save lives. Machine learning algorithms can analyze medical data and predict whether a patient has a high risk of heart disease or not. Actually, my present study uses a different classification algorithm to improve prediction accuracy and assist healthcare professional decision making. Actually, many of them done with heart disease prediction using machine learning algorithm, but they didn't give proper accuracy level. And moreover, they have given lack of feature selection, prediction, and categorization of heart diseases. Hence, an efficient machine learning based genetic algorithm is required to improve prediction and classification accuracy. Related studies, actually, to understand the existing research in heart disease prediction, several studies were reviewed. Many researchers have applied machine learning algorithms to improve early detection of heart disease. For example, some studies used logistic regression and decision tree algorithms and achieved moderate prediction accuracy. Other researchers applied advanced techniques such as random forest, support vector machine, and k nearest neighbors, which showed improved performance. In recent years, deep learning approaches such as artificial neural networks have also been used for better classification accuracy. Most studies used datasets like the Cleveland heart disease dataset and evaluated models based on accuracy, precision, recall, and F-score. However, many existing studies either focused on a single algorithm or didn't compare multiple algorithms effectively. Some models also faced issues like overfitting and limited feature selection. Therefore, the present study aims to compare multiple machine learning algorithms and identify most accurate and efficient model for heart disease prediction. And I have find out based on my related papers, I have find out 4 important research gaps. Actually, existing study, they didn't find out abnormal activity of cardiac is not achieved in the baseline algorithms. And the second thing, they didn't used for proper data set. Third one, and they didn't achieve what type of heart disease is this. And also accuracy is comparatively low. Then finding the problem statement. So we need an efficient data processing methods using enhanced decision support system and hybrid machine learning algorithms using recurrent neural network with 2-level classifier and genetic algorithm for predicting heart disease, and it will find out the type of heart disease also. Next, the objectives. So to analyze and pre-processing the data using enhanced decision support system, to extract the features using modified principal component analysis, to implement the improved genetic algorithm with support vector machine for predicting the heart disease, and the type of heart disease will be identified with the help of recurring neural network. Actually, my present study, that means my model having 3 phases. Phase 1, I have done with data pre-processing with the help of decision support system. And phase 2, I have done with the feature extraction using modified principal component analysis. And phase 3, in phase 3 only very important, here only my model identify whether the patient has heart disease or not, and if suppose the patient having the heart disease, and it shows which type of heart disease is this. So totally 3 phases I have done this study. I have taken data from Google website. Actually, the data set name is Cleveland heart disease data. Actually, the data set size is 6,124. Totally features are 76. Total features 76. After my feature extraction, I have chosen only 14, which is most important to identify the heart disease. For example, like age, sex, chest pain, serum cholesterol, resting blood pressure, like that. In phase 1, I have done with pre-processing. Actually, totally 6,124 rows will be inserted into the software. In that first, finding the missing data and dropping that missing values. And then the data will be converted into standardization. After removing the outliers, data will be sent to for feature selection. So totally, many, that means 76 features are there. But in hard disease prediction, we need only for 14. That means most important feature only enough to predict in the disease. So after feature selection, the data will be sent for training and testing split. So it will taken by 70% of the data will be sent for training and 30% data will be sent for testing. So after this TT model, finally it shows the patient having heart disease or not. So that will done by enhanced decision support system. Why I'm choosing enhanced decision support, that means decision support system for pre-processing, means it is accept both supervised and unsupervised machine learning model. It accurately classify whether the patient has presence of the heart disease or absence of the heart disease also. And it will be done by scaling, normalization, and dimensionality reduction also. Properly, it will finally, that means for giving the to whole data set, it will produce the result, what means normalized data. Normalized data only it given in the first model will be given only in the normalized data. So these are all the steps we have done with data pre-processing. First, we have to load the data, then find out the missing values and drop the missing values. Split the data into features and labels and make it in a group. And then these data will be converted into categorical variables to dummy variables. Split the data into training and testing test sets. Standardize the data. Finally, it fit into the transformation format for finding whether the patient has a disease or not, means heart disease or not. In the first phase, I have done with Python software. From this, first result is according to my data set, 35% of the minimum age people affected with heart disease, 77% of the maximum age people affected with heart disease. So the average is 56.59. And the gender exploration comparatively compared to female, male members have most of them affected with heart disease. Total data set, 56% of the rows have, that means 56% of the patients having heart disease and 44% of the patients does not have a heart disease. And then for performance, I have used some matrices like sensitivity, specificity, accuracy, F-score, true positive, true negative, false positive, false negative, precision, and recall. So I have compared with existing 3 different algorithms, but my model only given for the better result comparing in existing one. Then second phase is feature extraction. In the feature extraction, I have done with the principal component analysis. That means the original data. The original data will be modified into necessary features Total 76 attributes are there in the Cleveland dataset. After feature extraction, it will be converted into 14 necessary features. And I have used for this algorithm. It means these are the steps we have find out for in feature extraction. First, finding EGN value and EGN vectors. Actually, these are primarily utilized for dimensionality reduction, allowing models to focus on the most important patient data while ignoring noise. The fit transform method in machine learning is used to calculate the necessary parameters for a data transformation and apply that transformation to the data simultaneously.
Ma'am, I'm so sorry to interrupt, but your
Yes.
time is up. I'd request you to conclude your presentation.
Oh, okay. 1 or 2 minutes I'll take.
Oh, ma'am,
Um,
please do it as soon as possible.
Okay. Actually, in the third phase only, we have done with heart disease prediction, and it shows only that means which type of heart disease the patient has. Here, we have applied for recursive feature elimination and sequential feature selection for necessary data to predicting the disease. And in my model, three uniqueness having. The first one is how features are selected and represented. The second one is how we are going to select the features with the help of kernel function choice and training. Third one is the training data. This one only identify the patterns and distributions. So the same ROC and ASU curve we have mentioned. So totally our model have given 96.4 percentage. This one very helpful to the medical practitioner also in future enhancement. If we added with any one sensor devices, and it will give the better results. Thank you.
Thank you so much, ma'am. The session chair, do you guys have any questions for her?
I have one question for her. Are there any limitation in your study that you would like to highlight?
Actually, I didn't hear your voice. Please.
Are there any limitation in your study that you would like to highlight?
Message me in a moment, please. Actually, I think my mic is problem. Extremely sorry. I
Okay,
don't know what questions you are asking.
Okay, are there any limitation in your study? And
Yes,
you
ma'am.
would
Yes,
like-
ma'am. Yeah, implementation's done, ma'am, actually.
Yes, ma'am?
Yeah, we have used for hybrid machine learning algorithm, enhanced decision support system for data pre-processing, modified principal component analysis for feature extraction, and genetic algorithm and agreeing neural network for to finding the heart disease prediction, and it shows the which type of heart disease is this.
Okay, thank you.
Madam, can you elaborate more on the dataset you have used? Its size and all of that.
I have taken dataset from Google website only, but this model will applicable for any dataset.
What is the size?
6,124 only I have taken. But it is applicable for more than anything.
Okay, that's it from my side. Thank you.
Thank you so much, ma'am, for that interesting and enriching presentation.
Thank you.
Welcome. Now, I would finally like to conclude this session by sincerely thanking our authors for their excellent presentations and valuable contributions to this session. and all our participants for being a part of this international conference. I hope this session was informative and enriching for everyone. All the presenters will receive their digital certificates via email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the ICICT 2026 team. On behalf of the entire team, thank you for your continued support to the 11th edition and the previous edition. We look forward to welcoming you again in the 12th edition in 2027. Now, as a token of appreciation, I would like to present these certificates to our session chair on behalf of Team ICICT 2026 and Global Knowledge Research Foundation and partners. I would like to invite Ma'am if you could say a few closing remarks.
Yeah. Thank you to our presenter for their insightful and engaging presentation. And on behalf of the session chair, I would like to congratulate all authors for their valuable contribution to the conference. And we hope everyone enjoyed the discussion. That's all. Thank you.
Thank you so much, ma'am. Now I'd like to invite Dr. Sonali to give a few closing remarks of her own.
Yeah, I sincerely thank you, organizers of ICICT 2026, and congratulating you for this 11th conference. And I appreciate that you give me a opportunity to serve as a session chair. I also extend my appreciation to all the presenters for their contribution, and particularly they were spanning the um, content from the intelligence system in the various areas like healthcare, transportation, other domains. So it was very insightful and learning session for me as well. Thank you all of you for making this session very engaging and really meaningful. Thank you very much.
Thank you so much, ma'am. I extend my sincere gratitude to our session chair for chairing the session with great energy and for all of your valuable inputs and guidance throughout the session. I would now kindly request all of you to switch on your cameras for a quick snapshot for valuable memories to be posted on our conference website. Now that everybody has switched on their cameras, give me a smile. Thank you, everyone. It was such an honor to have all of you here. It was such a wonderful day, such a wonderful session. Thank you, everyone. Bye-bye.
Thank you so much. Thank you. Good luck.
Thank you.
Well, goodbye. Thank you.
Goodbye.